In section 13.3, we want to examine some other properties of curves. Let's say we have a curve C in three-dimensional space, and we want to be able to figure out certain properties about this, like how curved it is, and that kind of stuff. Now, in order to do that, we have to talk about a parameterization R of t. So we have a parameter t and a vector valued function r that gives us points on that curve. Unfortunately, when we use a parameterization R of t and look at its derivative, this includes extra information that is not necessarily relevant to the original curve C. In particular, in order to look at a tangent, we took the derivative and we divided it out its magnitude. This gave us a unit vector that is tangent to our curve. The actual derivative r prime of t includes extra information about the magnitude of this vector that isn't necessarily relevant to the curve C. Different parameterizations could change that actual value, that magnitude. And so you want to kind of get rid of the extra stuff from the parameterization that we're not necessarily caring about for our curve. Now, this is one way of approaching the problem. The other way is to try to find out a particular type of parameterization that is more useful for the particular curve. And we do that by first talking about arc length. So arc length, we're just measuring along the curve as if we were taking a tape measure along it, but we have to think about how to do this mathematically. Now, when we have a parameterization, we are really talking about parametric equations. So in the two-dimensional case, we have x equals f of t, y equals g of t, with some bounds on our parameter t from a to b. And if you remember, back in chapter 10, we had a formula for the arc length of a parametric curve. So here, the length of our curve is the integral from a to b of the square root of the sum of the squares of the derivatives. So we take the derivatives of each of these functions, we square those, and then we take the square, then we add them together and take the square root. Now, this is all we've really done here is we're looking at the distance formula. The distance formula here based off the Pythagorean theorem, and then we use derivatives and integrals in order to actually sum those up correctly. If we work in 3D, we recall that we have a distance formula here as well. And all we really need to do is put in an additional term. So if we have our parametric equations, x equals f of t, y equals g of t, and z equals h of t, still using a to b for the bounds on our parameter, we get this formula. So a very similar formula to what we had before, just with this additional z term or h prime of t term in our square root. Now, if we do have a vector valued function and we want to express it in terms of the vector value function r, we can do that. So here, our vector value function r of t is, we can either write it as f of t, g of t, h of t, or if we're working in 2 dimensions, we would just use f of t, g of t, or we could theoretically even work with higher dimensions and have more functions. We're still going to keep the same a to b limits on our t, and we want to basically turn these formulas into a formula in terms of r. And what we can notice is that these square roots are actually just the magnitude of r prime. When we take r prime, remember it has components of f prime, g prime, h prime. when we take the magnitude of that vector, we end up just using the distance formula essentially to sum the squares of all the components and take the square root. And so really all we're doing in both of these cases is integrating the magnitude of r prime. And so now we have this formula for our arc length in terms of the parameterization itself. The advantage of doing this is that the arc length, even though it looks like the parameterization is in the formula, it really doesn't depend on the parameterization itself. All it does is depend on where the starting point and the ending point. Not the A and B specifically, but what point you get when you plug A and B into our formula. So R of A is going to be a point, R of B is going to be a point, and if we have any other parameterization and we take the arc length from between those two same points, we will get the exact same arc length. And that's the key point to all that we're going to be doing with this concept. But before we even get started on that, let's work out a few examples. So here we have a curve given as a vector valued function. We're taking the arc length between t equals 0 to t equals 1. All we need to do is differentiate it. So the derivative of 2t is 2, derivative of t squared is 2t, derivative of 1/3 t cubed is going to be just t squared. We need the magnitude of r prime. So remember, we're just taking the square root of 2 squared plus 2t squared, which is 4t squared, plus t squared squared, which is t to the fourth. And normally these are going to be kind of tricky to actually integrate. The actual problems that I'm going to be asking you to do will be ones where things will simplify in a way that we can actually do the integration. In particular, in this case, we can recognize that what's under the square root is actually already the square of something. It's in fact the square of 2 plus t squared. And since 2 plus t squared is always positive, we don't have to worry about canceling the square root with the square. It just turns into 2 plus t squared. If this could be negative, we might have to have absolute value signs there. And so pay attention to that kind of stuff. Don't just cancel the square root with the square and think we're all good. We have to make sure we have positive stuff in there. The arc length is just going to be the integral from 0 to 1 of this magnitude. I'll just go ahead and write that in here, at least this first time. So we're taking the integral from 0 to 1 of this 2 plus t squared. That's a pretty simple one to integrate. Integral of 2 is 2t. Integral of t squared is 1/3 t cubed. When we plug in 1 and 0, well, the 0 just gives us 0 overall. So really all we're doing is plugging in 1. We get 2 plus 1/3, which is 7/3. That's the length of this curve from t equals 0 to t equals 1. Let's do another curve. This time it uses some trig. But the process is going to be the same. It's just going to be a little bit more effort to actually compute all that we need to compute. So again, we start with the derivative. Derivative of cosine is negative sine. I'm just going to go ahead and use angle brackets here. Derivative of sine is cosine. Derivative of ln of cosine. Now this one we have to use the chain rule. So we take the derivative of the natural logarithm is 1 over the inside. So we end up with a cosine of t on the bottom. But then we have to multiply this by the derivative of what's inside. Derivative of cosine is a negative sine. So let's just go ahead and put on top. Before we go any further with this, I'm going to go ahead and simplify the sine over cosine. Sine over cosine is just tangent. So we have negative sine t, cosine t, negative tangent t. but we do need the magnitude of this thing. So we're going to take the square root. All the negatives are going to go away, so we'll have a sine squared plus cosine squared plus tangent squared. Of course, we have our Pythagorean relationships that allows us to simplify this. Sine squared plus cosine squared is equal to 1. So really, we just have the square root of 1 plus tangent squared. But we can even go further than this. 1 plus tangent squared is secant squared. So we're really just looking at the square root of secant squared. And of course, now we want to think, can we cancel out that square root? Is the secant ever negative in the interval that we're looking at? Well, our interval is from 0 to pi over 4. 0 to pi over 4, that's all in our first quadrant, and all of the trig functions are positive in the first quadrant. So, yeah, secant is positive there, and we can cancel out the square root. So our arc length is now going to be the integral from 0 to pi over 4 of our magnitude, which is just secant. Now this is a function whose integral is a little bit tricky to get if you don't already know it. So this is one where I'd expect you to go ahead and look up the formula. There should be a table in the back of the book that has it. But the integral of secant is the natural logarithm of the absolute value of tangent of t plus secant of t. Of course, we're going from 0 to pi over 4, and the absolute values won't really matter here because we will only be plugging in positive, or at least positive numbers or zeros overall. But we'll just go ahead and put them in. So natural logarithm of tangent of pi over 4. Tangent of pi over 4 is 1. Secant of pi over 4, remember cosine of pi over 4 is square root of 2 over 2. Secant is 1 over cosine. So 1 over square root of 2 over 2 is just square root of 2. Then we subtract the natural logarithm of tangent of 0, which is 0, plus secant of 0. Remember, cosine of 0 is 1, and secant just flips that upside down, so we still stay at 1. But then we have the natural logarithm of 1, which is also 0. So overall, our answer here is the natural logarithm of 1 plus square root of 2. That is the length of this particular curve on this interval. Now that we've defined the arc length of a curve, or at least given a formula for what that arc length should be, if you want to think of the arc length as already being something we should have known, what we want to do next is use that arc length in order to create a parameterization of a curve that is kind of specific to the curve, that is kind of inherent to the curve, that doesn't have extra information that the curve didn't already have. And in order to do that, we're going to define a function that will tell us the arc length at any given point. So let's say we have our curve C with a parameterization. Just going to write para r of t. We are going to choose some starting point. Fortunately, this does require that we make some choice about our particular curve, but ultimately, what we're going to be doing with it won't get rid of our choice of starting point, but it won't be such a big deal that we've made that choice. But we're really just looking at some curve here. We've got the C. We pick some point. Maybe we'll even say it's point A. We have a point A that's on there that we chose as a starting point. We do need to determine what value of t gives us this point. So we'll say here that t equals A is the the value that we plug into our parameterization to get that point. But the starting point is not little a, it's the capital A. We're picking a point, not a value of t. We are going to define what we call the arc length function. And we're just going to use the formula we had for arc length from before, but modify it slightly. So here we have a function, s of t, that is the integral from a, so our starting point, or starting value, you might say, of a to the variable t, and we're using a different variable inside here because we do want the t to come on the outside to make it a function of t. So we're just picking u as kind of a dummy variable. But it's just the formula for our arc length, just with a different variable inside here, and with t as one of our limits. And what this is really going to be doing for us is it's going to give us a new parameterization for our curve. And the way we have to do that is consider s as a variable. Kind of abusive notation here to call the variable the same as the function, but that's the way we kind of do it. So we want to use s for this parameter. And in practice, what we'd be basically doing is finding the formula for this integral, making s equal to that formula in terms of t, and then we're going to take that formula and we're going to solve for t. So instead of s being a function of t, we're going to get t as a function of s. And once we do that, we can go ahead and plug that value of t into our parameterization r, little r. And that composition is then essentially just going to depend on s. We could say, we could give it a different letter here. Basically, if we plug a value of s in, we get a value of t. That gives us a value of our curve. That gives us a point on our curve. But we'll just say that we have a particular parameterization, capital R of our curve, that has the parameter of s. Now, what is the whole point of this? Well, this parameterization tells us how far along the curve we are. If we pick a particular point on our curve, and the arc length here is s, then the parameter that we have to plug into r is exactly that s. The parameter that we use for capital R corresponds exactly with the arc length from our starting point A to the point on the curve. In fact, we can actually say that the starting point A is r of 0, because the arc length from A to itself is 0. So we're using this information of arc length that doesn't depend on the parameterizations, but is an inherent property of the curve in order to define a parameterization that is very closely related to properties of the curve itself. This will make a little bit more sense when we put into practice. So let's look at problem 16. They give us a curve. They don't really tell us what the curve looks like, but they give us a parameterization. They want us to find an arc length parameterization. Basically, the kind of parameterization we have here, but they actually did pick the starting point for us. Once we pick that starting point, the arc length parameterization is pretty much set. The only thing it could possibly change is which direction we go around the curve. In fact, we should probably label here that on our curve that we're traveling that direction if we wanted to be more precise about it. So here, if we pick bigger values of s, we find points over here, and points on this side of A will have negative. So even though we want to think of arc length as a positive value, we have to consider them negative if we're going to get points on this side of A. But let's see that in practice. The first thing we need to note is what is our starting value of t? They gave us the point 1, 0, and we want to figure out what particular value of this parameterization here, what value of t corresponds to the point 1, 0. Now, they did pick one that makes it a little easier for us, so we can kind of guess this one. If we just take t equals 0 and plug it in here, then we get 2 over 1 minus 1, which is 1, and then 0 over 1, which is 0. So t equals 0 is our starting value for this starting point. We then go ahead and differentiate r, because we need to find the arc length. And that's the first step of finding the arc length. Now I'm going to kind of skip some of the steps here. We do have to use a lot of our differentiation rules. We're using the quotient rule for both of these. The first component turns into negative 4t over t squared plus 1 squared. Our second component turns into 2 minus 2t squared over t squared plus 1 squared. We then need the magnitude of this, magnitude of r prime. I'm going to go ahead and put a square here so I don't have to worry about the square root for the moment. That'll just save me a little bit of writing. But I need to square this. So we have 16t squared over t squared plus 1 to the 4th power. Then I square this thing. So that's squared on top, and this is to the 4th power on the bottom. Of course, we can go ahead and pull the t squared plus 1 to the 4th power on the bottom out. So essentially just put everything over that same value. We're going to go ahead and expand out what we have here. We have a 16t squared. This becomes a 4 minus 8t squared and a plus 4t to the 4th. And that simplifies a little bit. The 16t squared and then minus 8t squared, those combine. And ultimately we get 4 plus 8t squared plus 4t to the 4th over t squared plus 1 to the 4th. As you can kind of notice from what we did here, we got 4 minus 8t squared plus 4t squared by squaring this 2 minus 2t squared. And if you notice, the only reason why we had a negative here instead of a plus was because we have a minus sign there. This, what we have now, has a plus instead of a minus. So really the top is just the square of 2 plus 2t squared. In fact, we can even simplify this more because we could pull the 2 out. If we pull the 2 out, we get a 4, and what's left is a 1 plus t squared squared. Well, we already have t squared plus 1 to the 4th on the bottom. So that square can actually cancel out 2 of the t squareds plus 1s from the bottom. So actually, we get 4 over t squared plus 1 squared. And then one last step, because this is not the magnitude, it's the magnitude squared. We take the square root. So maybe I'll write it over here just for space. The magnitude of r prime is going to be the square root of that. We don't have to worry about any negatives here because the t squared plus 1 is always positive. So the magnitude here is 2 over t squared plus 1. Our arc length function, s of t, is going to be the integral from our starting value of t to just t. we're going to put in this function, but we're going to replace t with our dummy variable, which we'll go ahead and use u because that's what the book did, though we could use whatever letter we want there technically. We do have to remember how to integrate 1 over u squared plus 1. If you recall, that is actually the inverse tangent of u. The 2 there is just kind of sticks around for the ride. And if we go ahead and plug in t and 0, we get 2 inverse tangent of t, and then inverse tangent of 0 is 0, so that's all we need to do. Well, at least that's all we have to do for now. Because what we need to do now is realize that this is our new parameter s in terms of t. We need to solve this and get t instead in terms of s. Now this one's not too bad. All we need to do is divide by 2 and then take the tangent of both sides. So we end up getting tangent of s over 2. That is our t value. And that's the value that we're going to go ahead and plug in to the t's that we have in this formula. So capital R of s, our new parameterization, is going to equal 2 over tangent squared of s over 2 plus 1 minus 1. That's our first component. Actually, let's go ahead and erase those. There. I'm just going to write it in our angle brackets. Our second component is going to be 2 times the tangent of s over 2 over tangent squared of s over 2 plus 1. Now that looks really ugly, but they actually chose one that works out very nicely for us. We can use some trig identities here. Tangent squared of something plus 1 is just the secant squared. And then secant squared on the bottom is going to turn into a cosine squared on top. So the first thing we do is change this into 2 times cosine squared of s over 2 minus 1. And then we do the same thing over here. We'll get 2 tangent of s over 2 times cosine squared of s over 2. So we'll have a 2. We'll have a cosine of s over 2. But the other cosine of s over 2 will combine with the tangent of s over 2 and turn into a sine. So already quite a bit of trig identities that we've already used. But we're going to go even a step further with trig identities. If you recall the double angle formulas and the half angle formulas for sine and cosine, this right here is just cosine of s. Because if you looked at cosine of 2 theta, it's 2 cosine squared of theta minus 1. Or at least that's one of the forms of it. Here, instead of using 2 theta, we have just s, so we get s over 2. Same thing over here. If we look at sine of 2 theta, we get 2 sine of theta cosine of theta. And so this over here is just sine of s. So we actually get a very nice formula. And in fact, this is one situation where this reparameterization, the arc length parameterization, actually sheds more light on what curve we're talking about. Because if we recall, this is just the parameterization of the unit circle. This curve that we had originally is just a parameterization of the unit circle. And that didn't really match up, but imagine it did. And if we actually talk about what a particular value of R of s is, R of s is literally just the point on the curve where this arc length is s, or since we're using radians, this angle is s. So this arc length is equal to s here. All right. So, as you can tell, this is a fairly lengthy process. There's quite a few steps involved here. And I'm not going to lie, this is generally a pretty complicated process. And this was a very nice example of the process. What things can go wrong here. First of all, when we're taking the magnitude, we generally get square roots. In the examples we've looked at so far, the square roots were able to be canceled out. That's not always the case. And the problem is that when we do integrals, if we have square roots in there, it can tend to make things really hard to work with. In fact, it's possible to be impossible to work with. If we ran into something like the integral of the square root of t cubed plus 1, this is not a function that can be integrated to get a very nice function. In fact, we can't express this integral in terms of our normal functions. In other words, it's not what we call an elementary function. We can't write this in terms of square roots, sines, cosines, exponentials, logarithms, any of that kind of stuff. It's simply not possible. We can prove it's not possible. So we could have a very big problem when we actually try to take this integral. And even if we can take the integral, there's no guarantee that this formula, s equals whatever this integral is easy to solve, or even really possible to solve without some really big leaps in logic. So there's a lot of steps here that could have been a lot worse than they turned out to be. So in general, we're not going to try to do this, find these arc length parameterizations. In general, they're just too difficult to really find. But we are going to make use of the fact that these do exist. There's nothing in this process that, in a theoretical sense, doesn't ever work. We can always take the integral, we can always solve, as long as we have a one-to-one function here. And so we can always find this arc length parameterization in a theoretical sense, not in a practical sense. But we're going to make use of the fact that we have this ability in actually constructing some formulas in the next video. But we'll then proceed to actually derive some formulas that will allow us to kind of skip some of this process. So I'm going to leave that for here and see you in the next video.